So today I'm going to give you an overview of a project that we've been working on here at NTGS for a couple of years now to get a better understanding of the Pine Creek origin, the geology, and the stratigraphy of all the units that make up the origin. And so this is a project that we started in 2023. Um, we're working in this terrain in the Pine Creek area to better understand what is a terrain that has a history of successful mineral exploration, extraction, and has potential for quite a number of other critical minerals within the Pine Creek origin. It's also very close to Darwin. It's very easily accessible. Um, this terrain has despite this long history of exploration, it's last been really looked at in terms of the geological history back in the 80s and early 90s. And so what we wanted to do is take a new modern, fresh look at the rocks using modern techniques, modern tools that are available to us now, try and get a better understanding of the lithostratigraphy, to characterize these rocks, to evaluate how they correlate across the terrain and how they correlate potentially with other terrains that are related of the same age. We'll do this to get a better understanding of the evolution of the origin and place all of this mineralization in the origin into this new understanding of the geological framework. So this is a map of the Pine Creek origin. For scale, you have Darwin up here in the northwest, Catherine down here in the southeast. The geology that's plotted on this map is the outcropping geology of the Pine Creek origin only, and it's over this dark khaki color. That's the extent, the interpreted extent of the Pine Creek origin um, province scale. The Pine Creek origin has been historically divided into three major domains. This is based on the metamorphic grade of these different areas within the Pine Creek origin. We have the Litchfield domain in the west and the Nimblewood domain in the east, which have higher grade rocks, amphibolite, maybe sometimes even granulite facies rocks, whereas the central domain in the middle here tends to be mostly green schist or subgreen schist facies rocks. Also plotted on this map are these red dots that you see all over the place, and these are our mineral occurrences from the NTGS mineral occurrences database. And this is for the entirety of this part of the top end. And as you can see, the central domain has an extensive amount of mineral occurrences throughout it. So this is one of the other reasons that we're interested in doing an additional look at the stratigraphy of the central domain and of the Pine Creek origin. So very, very broadly speaking, in terms of the geology, um, the whole area is underlain by Archean rocks. So this dark brown here is Archean, and you see these popping up as the number of inliers underneath the Pine Creek origin. And then on top of that, there are a couple of major packages of rocks. The two big, most voluminous packages of sedimentary rocks are this 2.02 billion year old package called the Woodcutter supergroup and a younger package called the Cosmos supergroup that's about 1.86 billion years old. These have been intruded extensively by a number of igneous units, including you see some purple here and here. These are dolerites, as well as quite a large number of granitic units at about 1.84 to 1.81 billion years. Um, Economically, we have these mineral occurrences throughout the central domain, but between the two different supergroups, the Woodcutter supergroup and the Cosmos supergroup, these host quite a number of these occurrences, but there's differences in the different commodities that are present in each of these supergroups. With very importantly, within the Woodcutter supergroup, we tend to have this graphite and iron ore, and within the Cosmos supergroup, we have a large amount of gold. So the focus of our project here is to, um, aside from the big picture tectonic history, is to first off characterize the stratigraphy, characterize the rocks that are on the ground, and characterize their relationships between them. We've started out basically at the bottom of the stratigraphic column and are working our way up, looking at the Archean, as well as these two major supergroups that host a large amount of this mineralization, as well as a bunch of this igneous intrusions, the Zamudolerite, the uh, granitic rocks that have intruded post deposition of these supergroups. So today, in this talk, I'm going to talk about a lot of the new data that we've collected in order to characterize these units, including a large amount of detrital zircon data that we've collected, um, some work that we've done to try and characterize this unconformity between the 2 billion-year-old woodcutter supergroup and the 1.86 billion-year-old Cosmos supergroup, and some work that we've been trying to better understand some of the units within these, including the Beryl Creek Formation, which is at the top of the Cosmos supergroup here, and the dolerites. To do that, what we've been doing is going out and visiting a large number of the outcrops. We're trying to visit every single one of these units in outcrop form if possible. We're going to do that in order to understand what the rocks look like in outcrop, and how they relate to other rocks within the terrain. We're collecting large numbers of samples, and back in the office, we are collecting large data sets for each of these in order to provide baseline data sets for each of the units within the stratigraphy. These include things like petrographic characterizations, whole rock geochemistry, geochronology, and some isotope geochemistry. To date, we've released two big packages of work, including this record 2025-1, which is a petrographic report describing many of the units within these two supergroups. And we've also released a large number of geochemistry in our DIP 42. And that I believe we have something around 1,000 new geochemical samples that we have added to DIP 42. So I'm going to start and give you some overview of some of the highlights of that we have seen to date so far. And I'm actually going to start at at the top of the stratigraphy with the Zamu dolerite. And the reason I'm going to do that is because it turns out the Zamu dolerite and the dolerites in the central domain have a lot of important implications for the older stratigraphy. And so in order to understand this older stratigraphy, we first need to understand how old the Zamu dolerite is. Also, really importantly, is it actually a single eumagnetic unit? Now, historically, we have two major areas of this unit called Zamu dolerite in the central domain. There's these purple rocks in this area called the South Alligator Valley, and there's these purple rocks in the area called that I've labeled here as Burundi. Historically, basically everything that's a dolerite in this area has been called Zamu dolerite. But they're not exactly the same. So one of our goals has been to go out and say, hey, are these actually the same? Is everything Zamu? Or is this more complex than that? So turns out, yes, it is more complex than that. And so taking a look at some data from these two areas, here's just two example samples here. Um, First off, just the very first order observation, the rocks look different. In the South Alligator Valley, that's the area to the east, the rocks tend to be a lighter color gray. The ones in the Burundi area are a much darker unit, and this is reflecting a different feldspar component in the rock. So the South Alligator Valley have more plagioclase. We've also wondered, hey, if these rocks are not the same exactly petrographically, are they the same age? Do we have one mafic intrusion event that's spread across this entire central domain, or do we have multiple events? And one of the ways that we've gone about testing that is to try and understand the age. Historically, the Zamu dolerite, the historical Zamu dolerite, has been interpreted to be 1870 or 1.87 billion years old, based on a very small number of zircons that were dated a very long time ago. So one of the things that we wanted to do is provide a new, more modern geochronology to this to get a better understanding of using more modern techniques if we can really constrain the age of that. And this is the sample that had that zircon. Turns out, luckily, it also had bedelite in it, and bedelite is a great property that if you bedelite coming out of a dolerite, you can pretty confidently interpret as a magmatic crystallization age. So Simon Bedorkis at GA analyzed these on the shrimp for us, and this is some very new data that we have 1865 plus or minus 4 million years. That's exactly the same as the zircon, and it's confirming that the the dolerites in the east in the South Alligator Valley area are in fact 1.87 billion years old. But then the question is, how about these dolerites that are the darker, different phase, different looking rocks in center part in the Burundi area? Now, we collected a number of samples. We analyzed a number of different minerals, including apatite and titanite. And between all of the samples and between all of the minerals, we are consistently getting two ages. And this is an example of one of those ages, of one of those sets of data, but all the data are exactly the same. We have an older age at 2 billion years and a younger age at 1.81 billion years. Because we've done this in situ, we know that the younger age it's from apatite and titanites that overprint everything, and we also know the local field relationships indicate that can't be a crystallization age because the granites, for example, are that age and they are having cross-cutting relationships with this unit. So what that means, or what that suggests, is that older 2.0 billion year age is the age of this dolerite in the Burundi area. And as a result of this, we are in the process of redefining the dolerites in the central domain. So instead of having this one single Zamu dolerite, we're going to have two dolerites. The younger dolerite, the 1.87 billion years, will retain that Zamu dolerite name, but it's only going to be the rocks in the South Alligator Valley area. In the center, the 2 billion year old dolerite will be called Burundi dolerite. So now moving back down into the stratigraphy to look at the woodcutters and Cosmos supergroup, because there's this fair amount of economic interest in these rocks, as you can see by the historical mining, but also very importantly, it forms the Cosmos supergroup forms the front cover of this year's Ages poster. Um, we collected, in order to characterize the units of these different rocks, one of the tools that we collected is uranium-lead tetraidal zircon. And what we've noticed is that between the woodcutters and Cosmos supergroups, you have two very distinct tetraidal zircon patterns. In the woodcutter supergroup, and this is an example of a rock called the Mundeji sandstone, it's one of the units, but consistently across the board, we tend to have these very simple tetraidal zircon spectra, where you either have a bimodal distribution like this, where you just have two simple peaks, one at about 2 billion years and one about 2.5 billion years, or a unimodal peak that only has one of these. 2.5 billion year peak probably reflects the underlying Archean basement, which is also 2.5 billion years, suggesting that it's has a significant component of sediment derived from that local source. And that 2 billion year age is the same age as some local volcanics within those units. And so that's probably derived from that volcanism. Um, but across the board, we tend to have these really simple patterns. And here's another one with a unit called the Wildman siltstone, which is at the top of the woodcutter supergroup. And this one is one with just a simple unimodal age, 2.5 billion year age, probably locally derived from that simple Archean basement that's in the area. The Wildman siltstone, as an example unit here, is a carbonaceous and ferruginous siltstone mudstone. It's very commonly graphitic, and has times weight percent level graphite. And it's also commonly tourmaline bearing and kind of tourmalinites. So within the woodcutter supergroup, I mean, as with the Wildman siltstone, it can very commonly be graphitic, and this particular example has over 7 weight percent graphite. It's also a tourmalinite, so the rest of this rock is tourmaline. There's also other tourmalinites within different units of the woodcutter supergroup. That's interesting because it implies exhalative processes during formation of these supergroups. But as we move up the stratigraphy into the Cosmos supergroup, which is 150 million years younger, the lowermost unit currently signed to the Cosmos supergroup is this unit called the Coolpin Formation. Now, in the field, the Coolpin and the Wildman are very difficult to tell apart. They have a lot of very similar characteristics. They're both siltstones. They have variable amounts of sand. They're both commonly graphitic. They both commonly have tourmaline, including tourmalinites. I mean, there are some differences. There are some definitely some differences, but the similarities are very striking. So one of the questions is, how are these units related? Now, if we look at the chemistry, and these are plots of three example plots of geochemical elements, geochemical plots of sandy units within all of the units in the on the left in this box, that's the Cosmos supergroup, and these pink ones, that's the Wildman siltstone from the woodcutter supergroup. And these are three example elements, but just across the board with a lot of different elements, what you see is that Coolpen formation tends to have a very similar composition of the Wildman formation, which is distinct from the Cosmo formation, the Cosmos supergroup, which is another line of evidence that perhaps the Coolpen is more similar to the woodcutters. But then one of the really important lines of evidence here, and this goes back to the dolerites, is that there's the observation that in the central part of the central domain, in the Burundi area, the dolerites intrude the Coolpen formation. Now, back when we thought that dolerite was 1.86 or 1.87 billion years old, that didn't really matter. But now we also know that this dolerite that's intruding the Coolpen formation in the Burundi area is 2 billion years old. If the Cosmos supergroup is 1.86 billion years old, then that means the Coolpen formation can't can't belong to it. It's too old. Um, so as a result, one of the consequences of this study is that we're going to be redefining that unconformity and redefining these packages. So instead of having the unconformity here, we're going to move the Coolpen formation into and make it the uppermost unit of the woodcutter supergroup, and the unconformity will be above that. We're still testing this hypothesis, so it's still work in progress. So I don't want to, make it 100% yet, but it's looking like that. Now, continuing up the stratigraphy into the Cosmos supergroup, um, we have the Burl Creek Formation at the top of the Cosmos supergroup. And the Burl Creek Formation, as you can see in the map, is just the most voluminous, extensive unit exposed at the surface in the central domain. It's absolutely everywhere from Darwin down to Catherine and across from east to west. So one of the questions we have is this all the same thing? There's a number of tools and techniques that we've used to test this. The first, obviously, is going out and visiting outcrops across the board. We've gone from top to bottom and from east to west. It's pretty generically across the board, this monotonous package of this reddish siltstone sandstone. But there are variations petrographically, lithologically. There are definitely some variations. It's not exactly the same. One of the analytical tools that we've done is to look at the detrital zircon geochronology to see if they have all the same um, provenance across the board. And by and large, the detrital zircon spectra are very similar. They're distinct from the woodcutters. If you remember, the woodcutters had two clear bimodal peaks. Here we have a single peak at around 1870 across the board, and this older tail. What's different between different samples is that this 2.5 billion year peak, sometimes it appears, sometimes it doesn't. I think that's just related to variable amounts of this Archean basement in the Burl Creek Formation. But overall, the main source of sediment is probably pretty similar across the board. So we don't really yet, we might in the future, but we don't yet have a basis for dividing this unit. Now, one of the other questions is how does the Burl Creek it occurs here in the westernmost part of the central domain. How does it relate to the Litchfield domain? Now, if you remember earlier, I said the Litchfield domain has amphibolite and granulite facies rocks. Well, it turns out, if you go into the Litchfield domain, things that are mapped as Litchfield domain, you find Burl Creek Formation. I don't say Burl Creek Formation, it's unmetamorphosed subgreen schist facies sedimentary rock. It's not granulite facies. But structurally juxtaposed against that, with faulted context, you have rocks of any number of different metamorphic grades, ranging from all the way down to granulite facies. You have unmetamorphosed sediments, you have amphibolite facies, you have granulite facies, structurally juxtaposed. Also structurally juxtaposed with igneous rocks that are unmetamorphosed as well. What this suggests is that the entirety of the domain was not as a single package. um, granuli facies, but instead, whatever happened to create its current architecture um, happened after the main phase of metamorphism that it caused that granuli facies metamorphism in the Litchfield domain. We've continued, we've tested the detrital zircon spectra here. The detrital zircon of the Beryl Creek in the Litchfield domain is more or less exactly the same, so that provides evidence that it is the same unit. This particular sample, we only have one sample here, but it does have a larger Archean peak, but overall it's the same. And we've also compared it to that high-grade granulite facies rocks, because we want to know, hey, is that high-grade granulite facies rock, is that completely different, or perhaps it's the same unit? Now, these are old data, so it's at a time when we collected far fewer zircon data, so it's not 100% comparable. But what it suggests is it has a very similar spectra with a 1.87 peak and a older tail, which provides a hint that we were going to continue to test that perhaps these granulite facies rocks in the Litchfield domain are high-grade equivalents of the Beryl Creek Formation or something similar. So we've had quite a bit more than this, but these are just some of the highlights that we've seen to date that I wanted to share with you. So I will stop here, but I will be available afterwards if you want to have a chat.